So let's move on with my out of the world subtitle. So school districts on Mars, fuel depots on Jupiter, inimical dictators on Neptune. What combines all that? What combines minimizing energy? What do electrons, Buckyballs, maybe not all of you know that particular word, and orifices, what combines all that? And it's one principle, minimizing energy. You know, stable configurations always try to minimize the energy that is necessary to maintain these configurations. So an outline, it's quite, I guess, energetic. Should I use Carl's terminology? Yeah, it's quite a lot. Maybe I won't be able to accomplish all of it. But I will say a few words about well-distributed points on the sphere, and then start with our cousins, physics and chemistry and biology, that actually give us the problems. They supply us with what is needed for us to actually flourish. And I will talk about the mathematics behind all of these motivations. So, next topic, 4 evil dictators on Neptune. I'll actually present a mathematical proof. So those of you that were hoping not to see one, I hate to disappoint you. A journey to the school land planet. We'll talk about school districts. After all, it was in my subtitle. And some more serious section of my talk, separation properties of optimal configurations. And finally, the 5 evil dictators on Neptune. Okay, so well-distributed points on the sphere. What exactly does that mean? First of all, what is the sphere? You have 3 coordinates, height, width, and length. And when you square these coordinates and add them together, that should give you 1. That's what the unit sphere in space is. The distance to the origin is 1. And how do we distribute well points? And why is it such a difficult question? It's very easy for the circle, isn't it? What would you do? Just measure the circumference, 2 pi r, divided by, say, n, and that's what you have to walk across the circle at that length and just place a point. That's how you're going to get equally and nicely distributed points on the circle. Well, if it's so simple, why in the world would we even bother? Well, turns out that there is a good reason for it. There is a direction and there is order. Things that we really lose in 3D and higher dimension as well. So what we really need here is different approach. No longer just the intuitive, well-distributed is enough. So we really start talking about this quantity, energy. So we need to somehow measure what is the potential for work of a certain point configuration. Say we have 10 points on the sphere, or maybe 1 million. How are we going to distribute it? It's intuitively clear that we want to have every region of the sphere rich with points. So if we take some island on that planet, we want the number of points that fall there to be proportional to the area of that island compared to the entire area of the planet, right? So this is really what we're after. Turns out that we have actually right there a whole bunch of problems that start. One is best packing points. We will see this application in biology, and we'll say what best packing points are. Fekete, a Hungarian mathematician, and Fekete points are actually how electrons distribute. Logarithmic points, they come naturally from computer science and complexity of algorithms. One of the field's medalists, this is the Nobel Prize, I guess, equivalent in mathematics, raised that as one of the problems for the 21st century. You know, finding points that minimize the so-called logarithmic energy. And then there are the more general ones, risk points, that actually encompass all three as partial results. So let's move on to electrons. Suppose that we have n electrons. So I'm going to talk in general about the number of points, and I'll denote it with n, naturally, number. And electrons repel. Now, they repel the action between two charged particles. The force is proportional to the, inversely proportional to the square of the distance. And the corresponding potential the 2 points create is actually proportional to the reciprocal of their distance. So it only makes sense to define the energy as sum of all possible pairs of reciprocals. Okay, 1 over the distance between 2 points. And then sum this over all possible distances, and this is what the energy is. Actually, it was initiated with Thomson, and that's why it's called Thomson problem. At the beginning of the century, he was proposing the plum pudding model for the atom. Well, he was disproved very soon after that this model is not adequate, but still the problem has interest about minimizing this energy. And how will you do these? Here are 32 electrons and 122 electrons in the so-called equilibrium. Observe the cells on these will get back to these cells further down the line in my talk. Nice pictures, by the way, done by my scientific cousin, Jan Muzau, who was, at the time when I was working on my thesis, he was also at South Florida. He graduated before me and was working on this problem. And actually, somehow, I got into this drawn by my advisor at SAF. And we will see his name later. Okay, so what's the motivation from chemistry? See, this was an interesting problem, and a lot of mathematicians worked on it, not too many actually, but then everything exploded. It was in 1985 when the Fullerenes, the Buckyballs, were discovered. And I will say what Fullerenes are. Large carbon molecules, stable carbon molecules, brand new form of carbon actually. We know the diamond and we know the graphite. That is the third one, stable in nature. And they were discovered in 1985. 3 of the discoverers, actually the 3 researchers, Kroto, and Smalley, received the Nobel Prize in chemistry in 1996. Here's the carbon-60 model that Smalley, the late Smalley, had on his website. And here's a carbon-70. It turned out that once they knew what to do, they created a whole bunch of such molecules. Now, the story of this, the discovery of the buckyball, is really, it's like a nice, good novel. So Kroto was at University of Sussex, you know, I have a lot of extraterrestrial things in my talk. And he was studying chains of carbon atoms in intergalactic space. They saw that in intergalactic whole chains of carbon, but he hypothesized that they were created in a stellar atmosphere in red planets. But he couldn't prove it. At the same time, in the US, in Rice University, Smalley and Kroto were studying clusters of metal atoms. They were vaporizing some of these materials, and they were studying what happens with these clusters that are really not very temporarily, but using, this is the important part, I guess, the laser supersonic cluster beam apparatus that Smalley actually patented, that he created. So, Kroto, through Curl, asks Smalley to use this laser beam cluster, laser supersonic cluster beam apparatus, to actually test what happens if you vaporize. He was not interested in metal, he was interested in graphite. He wanted to know about these carbon compounds. So he came September 1st, 1985, just barely unpacked. They started the experiments, and of course they have two graduate students, Heath and O'Brien, do the mundane task of running in the laboratory. Boy, were they surprised. You know, they vaporize that stuff, they move it into, cool it down, in, I guess, helium, and it's an interesting thing. I'm not a chemist, okay? I give up. That's not my thing. But anyway, somehow they go to another chamber where a mass spectrometer shows that there's this huge molecule, 720 atom mass units. Now, one atom mass units is 1/12 of carbon-12. So this means that there are 60 such atoms in that molecule. You know, so Smalley starts asking himself, well, how is it possible and how will these combine? See, diamond is a lattice configuration, while graphite is planar configuration. You know, you just have layers of layers of layers of, you know, molecules. But actually atoms. But this molecule has to be a spatial one. And it cannot be anything of a lattice. Okay? So he starts playing around with pentagons and hexagons. I'm giving up a little bit of my talk. And he comes up with the form. You will see it later. Well, we already saw it on the previous slide. Now, think about it. This is September 1st. September 13th, the paper is submitted to Nature. Isn't this amazing? We all know how long it usually takes to make a discovery. 13 days? 2 more months, and it appears? Oh my God, it's big. Okay, why Fullerenes? Well, we have Richard Buckminster, Bucky Fuller, one of the great inventors and a person with very high IQ, and I may say with a taste for spherical domes. So this is the Montreal biosphere. Here's another one that is more well-known, Epcot Center. Okay? And because they were fascinated by these structures, and they obviously were related to the hexagonal soccer ball design. Of course, they called it after Buckminster Fuller. Nanotechnology. Turns out you can grow carbon molecules. You can make them even into nanotubes. Okay? You can make them long. You can dope some metal atoms. And as a result, you get this really strong, very, very tiny wire. Okay? It's on a nanoscale. It's invisible. But at the same time, the tensile strength is, what was it, 200 times the steel, 100 times higher than steel. You know, its conductivity is just as good as copper. And whenever you actually compress, that's a spatial molecule. When you compress it, it becomes much harder than diamonds. Not only that, you can place inside things and use it to actually deliver medicine. It's just unimaginable what you can do with Fullerenes. Okay, now the good news is that I have at least my, turns out I can't read that. It's too high, the angle is sort of difficult, but I have it here. So, what's the motivation from biology? The so-called Tammes problem. In 1930, Tammes, who was a Dutch botanist, asked the following question. He observed that in pollen grain, the orifices are distributed in a very nice way. And he asked the following question. How many? Well, if we have n circles of the same radius on the, well, spherical caps, polar caps. Spherical caps on the sphere, what is the largest possible radius that you can get so that you can pack these spherical caps? And that's a mathematical question, very interesting. Turns out it has a lot of applications in coding theory, one of the ways. So, what is the largest diameter of n equal circles that can be packed on the surface of a unisphere without overlap? So this is his question, and as you can see, here's the pollen grain, and here's that mathematical construct that corresponds to the question. Some more images. Another interesting thing I found on the internet when I was doing this, actually this talk is presented at many, many different occasions. But this is about the Starshine 3 satellite. And this is a satellite that was sent in orbit. And what they did to popularize science was to put 1,500 mirrors on that satellite. And when it actually came back to Earth, it was very well visible, and they actually had kids track down that satellite. It was a good, I guess, additional added benefit of the entire project. But the interesting part, of course, is how are these mirrors placed? You want them in such a way that they are somehow uniform. Okay, the mathematics behind. As I pointed out, you have this, maybe that's a better, you have this reciprocal to the power s. That's my parameter. So we consider not just the sum of the reciprocals, but also the sum of the reciprocals raised to certain power s. Turns out that when s is 1, you get the Thomson problem, you get the electrons. When S is infinity, you get the best packing. What happens when S is infinity? Only the closest one will contribute to the energy, and you want to make the points that are as close as possible to each other. You actually want to spread them apart, and then you will minimize energy. And when S is 0, these are the so-called logarithmic points, but then you have to do slightly different. You have to take a logarithm. Now, sum of a logarithms is logarithm of a product, and we will mention that a little later. So Tammes problem, S is infinity, as I pointed out. The solution is now only for the numbers from 1 through 12 and 24. It's very interesting. For 4, you have a regular tetrahedron. We will see that the regular tetrahedron is actually a solution to any problem minimizing energy problem. We will prove it. For 5, 6, we have north, south, and the rest of the equator. For 8, that is the skewed cube. The cube is not the best actually solution. Think about the cube. You have 4 vertices down, that's a square, and then a square on top of it. Now twist that halfway, and then get them closer, and you can make the distances larger. Okay? And that's actually the twisted cube is the solution. For N12 is another one of the Platonic solids, is the regular icosahedron, and it's a solution throughout. For 4, for 6, and for 12, the solution throughout is not difficult to establish, and that's because of you have good configurations that work nicely. Okay, they are so-called tight design on the sphere. I'm not going to elaborate on what that is. For 24, that was a very, very good paper back in 1961 by Robinson, and this is the snub cube. Okay, and the snub cube is a very, very special figure. So what about the Thomson problem? For n equals 4, that's the regular tetrahedron, we already know. For 5, talk about difficult, non-trivial problems, Carl. A 70-page paper of computer-assisted proof. You boil it down to verifying certain things that you can do with a computer. And that's a proof, all right? And again, that's a 1, 3, 1. North pole, south pole, and equilateral triangle. 6 is regular octahedron. 12, regular icosahedron. White's problem, the logarithmic points. Here, we have an IPFW connection. For 4, we have the regular tetrahedron. 12, in 96, Andreev proved that the regular icosahedron pretty much maximizes the product of all possible products of distance, of all possible pairs of distances. And then for 6, Kuleshov and Yudin proved that it's the regular octahedron. IPFW doesn't want to work. For N5, this is where Legge and Townsend and myself were lucky enough to prove it without a computer assistance and only for 14 pages. All right, so this is why this is one of the mathematical proofs that I was talking about. 4 evil dictators on Neptune. Okay, the thing about 4, why it's so important. There is a structure that you have 4 points on. First, it's 4 points always can lie on a sphere, you know. But among these, well, I lied. That's not true. It's true if they're not in one plane. If they're in one plane, they have to lie on one circle. So, anyway, my point is that there is a particular structure that has all 6 distances. When you have 4 points, you have 6 distances. And I have listed them: AB, AC, AD, BC, BD, and CD. And there is a structure where you can make them all equal. And there is this arithmetic geometric mean inequality. What it pretty much says is that the arithmetic mean, you add, in this case, 6 positive numbers, and you divide by 6. That's called the arithmetic mean. Now, if you multiply 6 numbers, if you think about measurements, say meters, that'll be meter to the 6th. So you have to take a root 6, what we call radicals, for those of you that don't like that word. Radical 6 of this in order to get the so-called geometric mean. Turns out that the arithmetic mean is always greater or equal to the geometric mean. Equality happens only if they are all equal. So, if we can say that this thing on the bottom is maximized when all these numbers are equal, okay, actually it's minimized, and then this will always be greater or equal to that minimum, and if they're all equal, we will achieve what we want, and we will have minimized the energy. So the problem boils down to maximizing the product, proving that the maximum occurs when they are all equal. And here, we get lucky. Okay? Because what could happen, and that's the proof, pretty much, you can place them, pick 2 of the points. If they lie, if the center of the sphere lies on the line connecting them, it's a separate case, you consider it separately. But other than that, 3 points determine a plane. Let's orient that plane, let's rotate the sphere so that this is a plane that is perpendicular to x. I think that's what I took. X actually equals 0, so that's perpendicular to the x coordinate axis. That's where the 3 points A, B, and the center lie. So they lie on top. And then we will rotate C and D in horizontal circles. We'll spin them. And we'll see separately, turns out, that maximum occurs when when you rotate C in that, on that circle. The largest that CA times CB can get is when C is right in the middle of that circle. Okay, when the two distances CA and CB are equal. Same goes for the other guy. Okay, so I can rotate one in the middle. Luckily, I can rotate the other to the other middle. And C and D, this is as large as possible when C and D are on the opposite ends of these orbits. That's not difficult to actually prove. Okay, if this is so, then I can always improve by moving one of these, C or D, unless they are on opposite ends. When actually CA equals CB and DA equals DB. But I can do this with any of the 2 points. I did it with A and B fixed. I can fix B and C, get the same, all of the other equal. Then what happens? You easily get that all of these have to be equal. I don't want to make a totally precise proof. Actually, I did for my favorite high school students in Mobile, Alabama, where I made that presentation, and this is what it is. Okay, but I'll just skip. If you observe right here, that's easy to see why the product is maximized when CA and CB are equal. What happens, this is a difference of the sum of squares minus that cosine theorem term, and then we have a summation. So everything boils down to A minus B times A plus B, that is A squared minus B squared, what we teach our 109, 113 students. And then that B, which is this guy here, Cm, Mk, and cosine of phi, if I can make that 0, I'm in good luck. Because then I don't have to subtract anything. I don't have to subtract that B squared. So this is the precise proof. But I move on to school land planet. Okay, distribution of Dirichlet cells, so-called school districts. With every point here, I will associate, so I have, in this case, 32 schools on the planet. Let's make up the school districts. What makes sense? You go to the school that is closest to you. So every point of these will be closest to one of the other. My battery is dying. Unfortunately, I couldn't find another one. So what happens, then you end up with these cells. They're called Dirichlet, Voronoi, and other names, cells. And what's interesting is that Dirichlet cells for 32 electrons in equilibrium are the tiles of the soccer ball. That's really fascinating result. Actually, it's numeric, so it's not really a result, but yeah, sure, they'll form a tile of a soccer ball. And actually, the vertices of the soccer ball, there are 60 of them, and they are precisely where the atoms in carbon-60 lie, in the buckyball. And now you guys understand the connection and why mathematicians are so interested in these problems that come from nature, that come from the other sciences. Because the sciences require answers. Where do they get them? They go to math. All right. Moving on. What is this? This is Dragnev's IPFW interview soccer ball 97. I see here two dear colleagues, emeritus professors. And there was another one, Professor Hamburger, who, when I came here to give an interview, I bought this small soccer ball that was, you know, one of these toys that you can squeeze, and it was easy to put in a suitcase and come with it here. But then we talked with Professor Hamburger. He was from Hungary. He is from Hungary, and we talked a lot. And you know, coming both from communist countries, he must have felt compelled to tell me a whole lot of his stories related to communism. And among the other things, I told him that I was born in Varna, the Black Sea. And he knew Varna. He actually, I think, has been there. And he said, oh, no, you're staying in the guest house. There is a swimming pool. That's where I stayed. You have to go and get a swimming suit. I said, well, you know, no, you have to. So he took me to Walmart, pretty much forced me to go there. And yeah, I saw a big, good soccer ball. And I said, I need to take this for my talk. So I'm buying this soccer ball, and he's looking at me. Hey, are you going to play soccer? Now, this is March 31st in Fort Wayne, and it was cloudy, rainy. Boy, no way I'm going to play soccer. But I say, hey, sure, tomorrow I intend to. He was like, wow. I don't know what he thought about it. Anyway, I did come to that talk, right? Remember that? With the soccer ball. It worked. Okay, more soccer ball design. We have other of these tiles. Well, why are some of them blue and some of them red? What is special about the red ones? Pentagons. And the others are hexagons. Yes. Well, is it possible to create a hexagonal school land on the planet? Elaine, what do you think? You're not a mathematician, that's why I'm asking. You have no idea. Take a guess. Yes? Yes? I had to do it. But mathematicians always ask, why not? That's our nature. We don't just take for granted that you can't do it. Well, there is this, this is graph theory people that I'm giving this talk to back in '97, because I did prove that there. So you have Euler's formula, and Euler is the father of graph theory. And Euler's formula says that the number of faces plus the number of vertices minus the number of edges in a polyhedra is always 2. On a convex polyhedra, I have to say what a convex polyhedra is, but a school land planet, tiling, will be a convex polyhedra. Okay, so 2 examples. The cube has 6 faces, 8 vertices, and 12 edges. 6 plus 8 is 14, minus 12 is 2. And soccer ball has 32 faces, 60 vertices, 90 edges. Add the 32 and the 60, 92 minus 90 is 2. Turns out that this is true in general. Okay, so suppose we could have created that soccer land, hexagonal soccer land. Well, what happens is then we can cut these edges in half and associate with every vertex a half edge. Then how many? Oh, I didn't say, but if you have a soccer ball design, every vertex would have 3 edges emanating from it. So that's why the total number of half edges will be 3 times the number of vertices, right? Because with every vertex there is 1 half edge associated with it. But at the same time, the number of half edges will also be twice times the number of total edges, right? I guess you agree with that formula, right? So what did I do? Just cut these in half, associate to a vertex 3 edges, that is 3v, and then just every edge is cut in half, so that's 2e. Of course, they're equal, and you end up with another interesting formula. 6f is equal to 2e. Now, how does that come around? Well, now, instead of cutting them in half, let's double them. Actually, we can count an edge, to one of the faces, and then the same edge to the other face, but the other side. So a left and right side of an edge. Then what happens, you will have a total number of 6f such half edges, well, maybe colored edges. So we color one side red and the other we color blue, and then we end up with every edge now has a, one side is red, the other is blue, so you have 2 of these colored edges. So the total is 6f. But then again, it's also 2e. The little algebra actually tells you the rest, okay? So we know that the faces plus the vertices minus the edges is supposed to be 2. But the faces from here are, okay, so from here, vertices, we can divide, we can get that vertices is actually 2f, and at the same time, e is 3f, right? So we do end up with f plus 2f minus 3f, which is 0. But that's not equal to 2. That's why it's not possible. Moving on. How many pentagons? We figured out we need pentagons. Turns out precisely. Now, here's where it gets good. Talking about graduate students, they figured out, Rachmanov and Sav, two of the professors, were working with Zhao in the office in the 90s because Smale asked this problem, and of course they got involved in it. And they were trying to figure out whether soccer balls have pentagons to start with. Now, we didn't have the internet to go and check. So, what did they do? Any guesses? Sent out the graduate student to Walmart. Buy one. Turns out exactly 12 I needed. A little bit more complicated kind of proof, but now we will divide number of pentagons and number of hexagons. Then actually we have a new formula. F is Fp plus Fq. Turns out the rest of the formulas are quite similar. This is 5Fp plus 6Fq is 2E. Still we have 3V is equal to 2E. This algebra is a bit more complicated. I'm not going to go over it. So I'll just pass on that. But at the end of the day, you end up that you get the same number of pentagons. I mean, 12 pentagons. A very ancient, actually, statue. And the interesting part is to figure out the pentagons. Turns out there is one right here, but it's not quite visible, so I'm going to skip. Some, humans were not the smartest species. Some other more ancient species actually figured it out. I'm sorry. What comes later, turns out that the pentagons, now that wasn't in the 90s, it was thought that any minimal configuration will bring only pentagons and hexagons in the Dirichlet cell decomposition. But then in the 2000s, the computers became really fast, and all that's being done, with few exceptions, is computer work. Algorithmic minimizing of energy. And what turned out is that the energy difference that is created between pentagonal structures and hexagonal structures actually requires a compensation. And the way to compensate that is to appear heptagons. So there are some heptagons, and this is 1,089 extremal points on the sphere by Ron Womersley from the University of New South Wales. So, separation of minimal energy points. Now, I told you this is the technical stuff, so I'm going to go faster now. And if I didn't overwhelm you by now, this is the time to do so. You have to get intimidated in a math talk. That's only natural. So, the question is, how do you measure whether a certain configuration is nearly optimal, at least a good one, well separated? You don't want them too close. Now, the fact of the matter is that a spherical cap, pretty much the area of a small island, think spherical island on the planet, will be proportional to the radius of this island squared. That only makes sense, right? Because think if it's really flat, it's going to be pi times r squared, right? Now, if it's a little not as flat, it's going to be close to that. Well, the distance, actually, you talk about Euclidean distance, spherical distance. I'm not going to get into that. But overall, if we have endpoints and they are surrounding nice neighborhoods, we have total number of n neighborhoods. Now, the unit sphere has, the surface of a sphere is 4 pi times r squared. It's actually 4 times the cross-section, big circle area. So if the radius is 1, then that's just 4 pi. So the natural thing, if you divide by n, you will have 4 pi over n pretty much, roughly, every island. But that's proportional to r squared. So a good separation would be square root of that constant over n, which is another constant over square root of n. So configuration is called well separated if that distance between the closest points, you consider the smallest possible distance between the points in a certain configuration. If it's greater or equal to a constant over square root of n, you have a well-separated configuration. And the classical case, this was established, classical case is when s is 1, the electrons case. This was established by Dalberg. For s bigger than 2, that's actually another one, was done by Kylars and Sav. And then there is a little bit of a story with the constant of separation when it comes down to logarithmic points. Rachmanov-Sav and his graduate student Zhao, they showed a separation with a constant of 3/5. Then Dubicus actually got 7/4. I did in 2002 a constant of 2. I was not aware of Dubicus' work. I knew that Ed had done some separation, and while Townsend, Legg, and I were working on the 5 points result, I thought, well, a separation would be a good thing. It will allow us to get something done. And I didn't have their paper with me. So I sat down and I pondered over myself. I knew they were doing something called stereographical projection, which pretty much is put a light source at the North Pole, think the Earth is transparent, and have a screen, flat screen down there. Whatever you project, whatever Earth looks like, that's what your stereographical projection is. So they were doing that stereographical projection, but they were picking a point that was in the South Pole of one of their optimal configurations, and I did something totally opposite. I picked the point in the North Pole. Now what happens when you're too close to that light source, you get thrown off to infinity. Okay, and that point, there is this extension in complex numbers that you talk about, the infinity, the so-called infinity. So turns out I got a better constant just by pure luck. And only then later I realized that this is a new result. And I met Ed at the conference in Portugal. He told him about it, actually presented it. And he said, well, you know what? I think someone else was working on that. And then he found the paper and sent it to me and said, oh, the bigger the constant, the better. And, he said, well, you beat him, so you got it right. But it's not so much the mere fact that I took it at the top. What's more important was that I ended up with a problem that had external field. Okay, now in all of these minimal energy problems, you can think about the energy of interaction, but suppose you introduce a charged particle somewhere else. Now that new potential that it creates totally changes the ball game. Now what I was doing was, okay, well, I send this point off to infinity. It creates, for the plane, an external field minimal energy problem. And then using that, I ended up with proving that constant. Now that same idea, later on, we started and worked with Sav in that other theorem. Now that's a mathematics theorem, okay? I did have to intimidate you, so that's this one. We proved in 2007 this is for multidimensional, not only just S2, but SD now. We're talking actually RD. In our linear algebra classes, usually we introduce for the first time to students the concept of not just 3D, but ND, n dimension. Well, in this case, it's DD, D dimension. So anyway, we did prove the separation, and this time it's not possible to project. We very quickly realized it's not doable. But here's the idea, and you guys, that's all you need. So you have endpoints that do good job, that are optimal, minimizing some energy. Now let's fix one of these endpoints and see what is the influence that this particular one has on the rest, n minus 1. So if we have 5 points, let's fix one and consider what happens as the influence on the other 4. Turns out that if the mass that I put in this fixed point, actually the problem reduces to an external field problem with 1/3 of a weight for that external field. And then solving one, you end up with solving the other. But the idea for the separation is the following. If we have something that really repels in that neighborhood, say in the North Pole, and we consider the rest, then what happens is that these other guys, no matter how many you choose, they will be in some neighborhood. It's called spherical cap, actually what is left when you remove that tiny guy on top. And that separation came naturally. Of course, we had to develop a whole theory related to Q external field problems. But at the end of the day, here you can see my result. When S is 0, we get 2 over square root of n, right? That constant. So I'll just have to skip a whole lot of stuff. This was about the approach. We move on. There is some movie that I want to show you. I'm not going to show that approach. Okay. So this is, now see, everywhere in the chain of command this semester, people conspired to make my life miserable and not be able to do research. You start with my chairperson taking a sabbatical. Then the dean has this good initiative that needs a lot of work. And then the vice chancellor has a P&T going to faculty affairs committee, other tasks. The chancellor and the president of the university decide to have birthdays. You know, pretty natural thing. But now as a result, we search. We have 2 searches. And I participate. Yet, they couldn't prevent me from getting something. So we did prove quite general theorem that Q minimal energy points are well separated. And this is the movie I wanted to show you. So hopefully something happens. Yes, we have a point that slides from top down. Okay? And when the charge is 1/3, when the charge is 1/3, you end up with a 1-3-1 configuration, that 5-point one that we got with Townsend and with Ley. And when it's 1, observe, when the external field is actually a different number, actually we get a different result. Now, of course, our theorem is large n and talks about separation. It's a different story, but it's a good illustration, and at least an interesting movie. Now, I was going to talk about dictators on multidimensional planet, but I see time's running out. So I'll skip that part. You know, this was a small proof. Maybe I'll just go over this theorem here and just tell you quickly what happens. Well, pretty much for 5 points, the result is the following. if you have an optimal configuration. You are either at the degenerate configuration, meaning that they lie on one plane, all 5 points lie on one plane, then it's easy to see that the regular pentagon has to be the minimal among all these that lie on one plane. There is a second possibility, and that's actually what the theorem says, that there is a vertex so that the distance to all 4 others is equal. Okay? And then the third one is the interesting part. The third one says that every vertex, the third possibility says that every vertex has a partner so that the distance to all the others is the same. So in 5 points we have 1, we have 2. Then the distance to the other 3 have to be equal. Okay? And that turns out to be a relation of equivalence, meaning that if A is equivalent, is mirror related to B, and B is mirror related to C, then that means that A is mirror related to C as well. So what happens very quickly from that theorem, one gets that for 5 points, you either are in the regular pentagon, or then a pyramid with square on the bottom, or a bipyramid where the 3 points are on the equator and one on top, North Pole, and one on the bottom. That is the ABC equivalence and DE equivalence. And then that's the 5 evil dictators. Some open research problems, or what happens, it's not known. Remember, when S was 1, it was 131 for 5 points. In that 70-page paper, there is another one when S is actually -1, also computer assisted. And there is our result for S equals 0. Now, what is computationally seen is that when S is less than, say, 16 point something, it is a 131 bipyramid solution. But when S gets larger, it is a 1,4 solution, with the 4 getting closer and closer to the equator. And when S is infinity, actually these 4 are on the equator. And that's easy to see that the best packing in this case is fine. So what happens? Can you give a proof of that? That's not known. And the other one that we try hard, but to no much success, usually these are difficult, 7 dictators. We don't know what happens there as well. Okay, well that's all.
Thank you, Peter. In commemoration of this spherical event, we have this plaque to present to Peter, which has the date and the notation of his selection as a distinguished lecturer. Congratulations. So I'm going to start and ask the first question, which is pictures that you borrowed from your friend showed the centers of those shapes. So are the centers of the pentagons distributed in the minimum energy positions of the 12 points for the 12-point minimum energy?
That was what was thought for quite some time, that when you have, say, 122, remember we had a whole bunch of different ones, that the pentagons are actually in the 12 icosahedron configuration. Now, that is what happens to about 1,000 points. Then that jump in the energy starts. Now, what happens there, Carl, is that you get either clusters or scars. So scars would be these chains of pentagons and heptagons. It's really interesting. Even on that picture wasn't there. There are more, there's more computational work done. but it tends to go into a 12 configuration, but even then, these cars can be long, and of course that will violate. But that was the idea. That's what was originally conjectured.
Also not math, or maybe it is. They don't make soccer balls like that anymore. For professional soccer, and then this was a big problem in the 2010 World Cup. They had a perfect sphere that did all sorts of unpredictable things, and all the players hated it.
Well,
He just created it. They're not using pentagon to hexagon.
now, this has something to do with baseball as well.
Yeah.
They have these, wherever you actually, the stitches, they create also some kind of a flow, and depending on what spin you give to a ball, the stitches most probably stabilize the ball. That's my explanation. Now, what will be interesting, and I know Carl is a vivid golfer, is what happens with the golf balls. They have these dimples, about 270 some, different number, but they are precisely nicely distributed on the ball. They have to be. So I don't know. I don't have a good answer, but I know I teach my honors calculus students about the Magnus force and the knuckleball, and how you get actually that in baseball, and how the Magnus force is the same thing that keeps the airplanes actually helps.
Well, thank you all for joining us this evening, and let's thank Peter once more.
Thank you.